Yeah, thanks for being here. I'm going to talk about our work on classical simulation of expectation values on noiseless random quantum circuits. And so first, let me thank my co-authors. Okay, yeah. So first, my co-author, including Sasha, also gave an online talk. Manuel, Marco, Zoe, who is my postdoc supervisor, and Robert Wang. And so let's just I'll give an outline of our results just in a nutshell. So our goal is to investigate the average case performance of a classical simulation algorithm, which is Pauli propagation, for the task of estimating expectation values in noiseless quantum circuits. So Pauli propagation is actually it's not something we invented, but is a recent framework for classical simulation that is to some extent very complementary to tensor networks. And the reason is that it's limited by different quantum resources. For example, while tensor networks are typically limited by entanglement, polypropagation is limited by, for example, by magic. And it also works very well for certain kind of noisy circuits. But our results complements this previous art by showing that even in regimes where you have possibly high magic and you don't have noise, this framework can still be very effective. And so our main result is that expectation values of random circuits can be estimated in polynomial time with constant error. So I will first discuss a few motivations behind this work. So the first motivation is coming from quantum supremacy experiments. These experiments are usually based on sampling, which is not what we do expectation values. But then sampling-based quantum supremacy has several shortcomings. For example, it's hard to certify classically, it is very sensitive to noise, and also these random circuit sampling tasks are very far from practical applications of most practical applications of quantum computing. So it is very natural to ask whether an analogous supremacy experiment can be designed with expectation values. And if one tries to do that, there are first some caveats, and the first one is that you cannot work with very shallow circuits, because for very shallow circuits, expectation values are easy to estimate just by some brute force simulation. And also you cannot take the circuit too deep, because if you take a deep random circuits, then expectation values will concentrate very fast toward zero. It's the so-called bar and plateau effect. But in principle, there might exist some intermediate regime in which brute force methods doesn't work, and guessing zero also doesn't work, and also no other classical algorithms work. And then even expectation values of random circuits could be the basis for quantum supremacy experiments. And our work is actually ruling out this possibility. So another motivation is coming from many-body physics, and especially chaotic systems. So chaotic systems are not random, but they're often modeled by random circuits, which closely resembles the one that we use in our work. And in the context of many-body physics, people care about expectation values such as correlation functions. And the other motivation is coming from variational quantum algorithms. So of course, the algorithm itself is not a random circuit, but is often randomly initialized. So often people start with initialize some circuits with the IAD parameters, and then they start training to optimize some loss function. So one natural question is whether the randomly initialized circuit from which we are starting is something that could already provide some quantum advantage, or whether it is instead classically simulable. And our final motivation is coming from the empirical evidence. So this family of algorithms has already been used, for example, along with tensor networks for dequantizing the IBM quantum utility experiment. So they work very well in practice, and we want to understand why they work so well. So yeah, we use terminology polypropagation, but actually there are also many other different terminologies used in the literature. People talk about polyback propagation, polypath simulations or polypath integrals, sparse polydynamics, operator back propagation. In other words, the technique is called the Louisa. But I wanted to stress that all these different techniques are actually part of the same framework. So of course there are small difference in the implementations and in the kind of approximations that are used to make the computation classically tractable. So it's called polypropagation because we work in the Pauli basis. So certain gates are very easy to model in the Pauli basis. For example, Clifford gates, they map a Pauli to another Paulis plus a phase. Also, we don't consider noise in this work, but noise is often very easy to model, especially if we have depolarizing or Pauli noise. What it is trickier are non-Clifford gates, for example, Pauli rotation, because they could possibly map a Pauli to a sum of two other Paulis, weighted by some trigonometric coefficients. So our algorithm works in the Heisenberg picture, and the reason is simple. We are working with the Pauli basis, and typical observable, often observables are very sparse in the Pauli basis. Sometimes you even measure a single Pauli. On the other hand, quantum states are not sparse in the Pauli basis. Even the computational zero state is supported on 2D Pauli operators. So it's mainly for a practical reason that we start in the Heisenberg picture. That is, we start from the observable and we backpropagate it towards the beginning of the circuit. So we apply these Pauli gates, we apply these gates to Pauli iteratively, and then based on certain criteria, we truncate certain Pauli operators. And finally, we overlap the result with the initial state, where the initial state could be either some classical state for which we have a classical representation, or one could also then use some hybrid approach in which you combine this approximate Heisenberg evolution with some quantum state you have in the lab, and then you can, at the end of the, so the algorithm, at the end of the algorithm, you get some Pauli operators, then you can also measure it on some quantum state you have in the lab. Okay, so one way to see this is through a tree-like structure. So we are starting here with a single Pauli operators, and as we apply gate, it is going to split in multiple Pauli operators, and in order to keep the computation classically tractable, we are going to truncate certain Pauli. So one possibility is to truncate Pauli operators which have small prefactors, and we call this coefficient truncation. The other possibility is to truncate Pauli operators that are supported on many, that act non-trivially on many qubits. And this is called weight truncation. And also when we consider the weight, we could either consider the weight or of a single Pauli operator, or take the cumulative weight over an entire Pauli path. And another possibility is also to make this, to explore this Pauli tree in a randomized way, for example, by using some Monte Carlo estimator that samples from the quasi-probability distribution, which is induced by this prefactor. But I mean, this is just for describing the framework. In this work, we actually only work with the Pauli weight truncation. So yeah, this is a reminder of the definition of Pauli weight. So it's the number of non-identity terms in a Pauli string. So for example, in this first example is 3. If you only have the identity is 0. And working with Pauli weight is very effective in two cases. It is effective for noisy circuits, both for sampling task and expectation values, and this was shown in previous work, and also for certain kind of random circuits, especially what we will define as locally scrambling circuits. but only if the task is estimating expectation values. Previously, as I discussed early with the sampling-based quantum supremacy, if you have no noise and you want to perform a sampling task, this is classically hard, and then we don't expect Pauli propagation to be very effective for this. So it's also very useful for analyzing and designing this algorithm to work with a specific formalism, which is the Pauli path integral formalism. And in order to define it, I will use the normalized Pauli basis, where the normalization ensures that when you compute the Hilbert-Schmidt inner product, you get either 0 or 1, depending on whether S and T are the same Paulis or not. So this is a basis. Then we can take any operator and expand it in this basis, as done here with this operator H. And we can also use this basis for expanding expectation values, that is overlap of two operators H and H prime. And this first expansion that you see here is just the step 0 of a Pauli path integral. So we consider some unitary U, which is actually the composition of L smaller unitaries. And then we consider these expectation values O, U rho, U dagger. And we rewrite it using this as a Pauli path integral. So the first thing that we do, we expand O in the Pauli basis. Then we do the same thing for this observable U dagger SL, U dagger L SL UL, and we do it iteratively L times. And this final big sum that we get is what is called Pauli path integral. And a very useful way to rewrite this is in the following way. So we write this as sum over Pauli paths, where a Pauli path is just a string of a vector of Pauli operators. Each Pauli path has a coefficient, which is called Fourier coefficient. And then there is a final product that depends on the overlap between the final Paulis that we get at the end of the path and the initial state. So let me also define the circuit model that we use in this work. We work with locally scrambling circuits. That is, the circuit can be, it consists in, all these single qubit gates that you see here are sampled IID from local 2D science. And in between this layer of single qubit gates, we have also arbitrary unitary, which can be arbitrary entangling, for example. And typically they have to have depth 1. So this is actually a special case of the circuit model we consider, because we don't actually need this IID single qubit gates to be there. We only need the layers to be invariant under single qubit IID gates. But this is just a subtlety, but it's important because, for example, brick wall circuits are included in our model, even though you don't actually have single qubit there, but the circuit distribution is invariant under single qubit random gates. And this is coming from standard properties of unitary designs. So, and we, in our proof, we use the fact that these single qubit gates are sampled from 2 designs, and we use it in the following way. So first of all, I wanted to recall that when you when you take the second moment of a Pauli operators evolved over a random unitary, and you take the average, then you obtain some sort of uniform superposition over all the Pauli operators, except so that there is a -1, because of course if P is traceless, both terms have to have the same trace. So you don't get identity in the second term if P was not identity in the first term. But what is relevant for our work is like actually the single qubit case of this expression, since we work with single qubit random unitaries. And what happens here is that if we take, for example, an X operator and we randomize it, in some sense it is mapped to some uniform superposition of all the other single qubit non-entity operators. And this effect is what we call scrambling. And scrambling has some implications on expectation values. So if you take, if rho is any fixed state, then the expectation of the observable X on rho is something between -1 and 1. But when we add randomness to the picture, then this the second moment of the expectation values is actually strictly smaller than 1. And the fact that this 2/3 is strictly smaller than 1 is crucial, because then when we repeat a similar reasoning on k qubits, we actually get a suppression which becomes exponential in the Pauli weight. And like the intuition behind this is that if now we have if now this Pauli operator P has weight k, and we are randomizing it with the single qubit unitaries, then each single qubit term has some probability smaller than 1 of overlapping with the state, and when when we iterate this over all the k qubits, we get an exponential suppression. And this is actually something not surprising, because it resonates with the fact that in the theory of variational quantum algorithms, you can have barren plateau even at constant depth if a cost function is global. So it's another way of rephrasing the same phenomenon. And also, this is more or less the same thing that happens without randomness, but with noise. So noise and randomness suppresses expectation values in a very similar way. And this is why we recover for random circuits some results that were previously shown for noisy circuits. So in particular, this idea of truncating according to the Pauli weight is something that was actually already present in quantum learning theory, specifically for learning quantum observables and quantum channel. So given an observable O expanded in the Pauli basis, we can consider the weight truncated version OK, where we only take the Pauli operator with weight less than k, and then on average over some random unitaries, for example, a layer of single qubit gates, the mean squared error that we do with this approximation is exponentially suppressed in the threshold k we have chosen. And this is closely related to the phenomenon I was discussing before. So what's the difference between this result and our result? The difference is that in our result, we are not doing a one-shot truncation, but we are propagating an observable through a quantum circuit, and at each layer we truncate. So we are doing many of these truncation, and the error could possibly grow with the number of the truncation we do. One other thing is that if for our result, we actually need to use a slightly tighter version of this inequality I was showing. That is, we need to work with the normalized 2 norm of the operator. This is a very important technical thing, because this 2 norm is going to be a conserved quantity, and this is very helpful for the proof. So, and indeed, our main result is that even if we truncate all the Paulis with weight k multiple times along this classical simulation, the error that we do is still the same, is still exponentially suppressed in the threshold k we have set. So, okay, so why the error is not growing with the depth? It is related to what I was saying before. The actual error is actually 2 over 3 to the k multiplied by this 2 norm, and this 2 norm is some conserved quantity, so this ensures that the errors cannot grow linearly with the depth. And one very important tool that we use in the analysis is that the different Pauli paths are orthogonal in the sense that their Fourier coefficient, they are uncorrelated when averaged over random gauge. So the time complexity that we found is then polynomial for constant error and success probability, where the success probability is over randomly sampled circuit, is over the randomness of the circuit ensemble. And if instead we want polynomial accuracy, that is epsilon equal to 1 over poly, then the runtime is actually super polynomial, but it is still like very advantageous, especially if we consider circuit with geometric locality, such as 1D, 2D, 3D circuits. So we have done several numerical experiments. Some experiments just confirmed our bound, and especially what we saw with the experiment is that our bound still works if you take any IID gates, possibly coming from different distribution. But when instead we drop the randomness assumption, we start seeing that actually the numerical results start deviating from the theory. So we did some experiments for trotter circuits, which they're relatively small scale experiments, but they actually indicate that polypropagation with weight truncation is still quite effective. It is less effective than in the random case, but still the errors seem to be below the theoretical bound, even though this circuit is not within our theoretical assumption. But I think that the most interesting experiments that we have done are about the training of a VQE. So in this case, we can see that as we start training and as we start deviating from the average case assumption, polypropagation becomes very inaccurate. And this is what you can see from this first plot. So in black, you can see the exact value of the energy, and in red, you can see the approximation with different truncation value, and this gap are quite big. What is more surprising is that instead we take the classical algorithm and we try to use it as a quantum inspired model for replicating a VQE. It still manages to find parameters values that are associated to low energy value. So in some sense, even when polypropagation is not able to anymore to replicate the quantum training, it seems able to perform an alternative classical training that still gives like very good solution for the optimization problem we are considering. But this is like something that I think deserves to be explored in more detail in the future. So yeah, I also wanted to promote our library that has been used for this work and also other follow-up work on Pauli propagation. And so the main contributor of the library is Manuel Rudolph. And although it's written in Julia, maybe a bit, so it's not the more friendly language. I think it's very well written and very good demo. So I encourage you to check it and also to use it for your simulations. And also, we have also other works on Pauli propagation, especially we have investigated the behavior of arbitrary noise, such as non-unital noise, including amplitude damping. And also we have some upcoming work on random circuit with symmetries, in which we drop these two design assumptions and we consider different distributions for the gates, such as more structured distributions. And we're also working on an extension to continuous variable quantum systems with Varun, who is in the audience. So I think that's some of the more interesting open problem here is to try to like go beyond this IAD assumption. So for example, I think that some randomness will be needed for the analysis, but for example, it would be very nice to take some random Hamiltonian and consider the time evolution or a Trotter circuit for the time evolution and try to replicate some of our results. And also another open problem is sampling beyond depolarizing noise. So for example, even though for deep noiseless circuits this would probably not work, maybe for shallow circuits one can prove something non-trivial. And another big problem are circuits with amplitude damping noise, for which the previous strategy for depolarizing noise doesn't carry. Yeah, so thanks a lot.
So I think we can take a couple of questions.
Hello, thanks for the talk. One question that I have here is that for the general Pauli propagation, it is based on the weight truncation for the Pauli, based on the Pauli weight, and that explains why only low magic circuits can be simulated. But for this particular case, like since you are simulating random quantum circuits which are chaotic in nature, so there is expected to be high magic generation. So what is the change from the general polypropagation that you have implemented here to be able to tackle like high magic circuits?
I think it's about the truncation strategy. So in this work, we truncate according to the Pauli weight.
Okay.
In the low magic regime, it's more natural to truncate according to the coefficient. That said, I think that it's also important to stress that if you take some very high magic circuits, then our method will be able to, at least with randomness, to estimate expectation values. But it could also be trivial because if you take a very complex circuits and you add randomness, then expectation values are going to be very close to zero. But still, I think that this sweet spot that I was showing in the motivation is a sweet spot in which you have non-trivial magic.
Okay. I have some more questions I'll discuss maybe after the talk.
Sure.
Okay, thank you.
So I think we can take one more quick question.
Hi, thank you for the talk. So in the VQA example, you showed that the higher weight threshold you choose, the more accurate the curve becomes, right?
Yeah.
But you also said that the training can still be good. What do you mean? Like the other parameters close to what you would get from an exact simulation with this method? Is that what you're referring to?
Yeah. Okay, yeah. Then it is still true that the higher the weight, the better accuracy you get. But this is still like a relatively small size simulation that is on 16 qubits. And to get something meaningful, we need the truncation cutoff to be 7, which is like half. So we have not done higher, larger scale simulation, but we believe that then you will need to scale the cutoff a lot. So yeah, and the black one is the black one is like some brute force simulation. Did I answer your question? I'm not sure.
I was asking that you mentioned that you can still get some good solutions. What do you mean by good here? That's what I was curious.
There is a caveat that I didn't say. So in order to obtain this second plot, we trained a quantum-inspired model based on the Pauli propagation algorithm. And then this model like found some angle parameters defining a quantum circuit. And then after that, we used a brute force simulator to check the value of the energy associated to these parameter values. And we saw that they were quite low. But crucially, we were relying on a final verification procedure that was involving, in our case, a simulator for larger scale, a quantum circuit. So it seems that Pauli propagation is able to find this low value, low energy state, but then it's not always able to certify the energy level efficiently. So the way we could conceive in the future of using this is by doing the training classically and doing one final verification procedure on a quantum circuit, which is still way cheaper than doing everything with a quantum circuit.
Thank you.
Yeah, thank you.